So we've talked a lot about how a tree is in some sense minimally connected because deleting even a single edge from a tree is guaranteed to disconnect that graph. And we can formalize this idea with the following theorem. So this is theorem 2.3.3. It says that the size of every connected graph of order n is at least n minus 1. In other words, if you have fewer than n minus 1 edges in your graph, there's no way your graph can be connected. So again, we're going to prove this using strong induction, the same way that we proved that a tree of order n has size n minus 1. Right, so we're trying to prove that if you have a connected graph of order n, then you must have at least n minus 1 edges in your graph. So let's prove this by strong induction. Remember, we start with the base case. We prove that if you have a connected graph of order n equals 1, then the size is at least n minus 1. All right, well, 1 minus 1 is 0. So if your connected graph has just one vertex, right, if the order is 1, then it has size at least n minus 1, because n minus 1 in this case would be 1 minus 1, which is 0, and every graph has at least 0 edges. You can't have fewer than 0. So this base case is sort of trivially true, but the induction step's a little bit harder. Okay, so to prove the induction step, let n be an integer greater than 0, and suppose that for any connected graph of order k, that graph has at least k minus 1 edges for every k between 1 and n. All right, we must show that the statement is true for n plus 1. So we must show that the size of any connected graph of order n plus 1 is at least n plus 1 minus 1, right? Replace your n's with n plus 1's. So we need to show that the size of every connected graph of order n plus 1 is at least n plus 1 minus 1, which is just n. Right, so start with the connected graph of order n plus 1, show that it has at least n edges. Okay, so assume that G is a connected graph of order n plus 1. Okay, well, if it's order n plus 1, its order is at least 2. It has at least 2 vertices. So let's let V be some vertex of the graph. Let V be any vertex of G. And let's consider what happens when we delete that vertex. Right, so in the last proof, we started off by assuming or deleting some arbitrary edge of the graph. Now we're going to start off by deleting an arbitrary vertex of the graph. So consider the graph G minus V. Okay. Now, I don't know if this V is a cut vertex or not. I don't know if this is going to disconnect my graph to remove V or not. Okay, it might not, but I can sort of draw a picture that looks like this. There's some number of edges coming out of V. Maybe there's one, maybe there's many, right? And let's just assume that deleting this vertex V is going to break up my graph into k components. Right now, k might be equal to 1. If it doesn't disconnect the graph, then I'll still be left with just one component, right? But it might be as many as, well, how many could it be? I guess it could be as many as n different components. Okay, and so we have that G minus V has exactly n vertices, because G had n plus 1 vertices, and now you've deleted one of them. So G has n vertices, and it's not necessarily connected, so let's suppose it has, we'll call it t different components. where t could be anywhere between one component if it's still connected, and n components if it completely disconnects the graph and you're just left with n individual vertices. Right, so we'll call this sort of subcomponent G1, G2, all the way to GT. Okay. So each one of those components is going to have a maximum of n vertices. Each component has at most n vertices, right? Because the most you could have is if you deleted this vertex and you just have one component left and all n of your remaining vertices are on that component. So they might have less, but the most that they could have is n vertices. So let's just say that Gi has ni vertices, with ni being less than or equal to n for all of these different components Gi. And so we have, well, this has n1 vertices, this has n sub 2 vertices, all the way down over here to n sub t vertices. And each one of these number of vertices could be at most n. If we know that this is a graph, okay, it's a component, so it's a connected graph with order less than or equal to n, well, that means that our strong induction hypothesis applies, right? Because our order is going to be less than or equal to n, which means I know that this connected component has at least, so I'll say greater than or equal to, n1 minus 1 edges. And this connected component is going to have at least n2 minus 1 edges. And this connected component is going to have at least nt minus 1 edges. Maybe more, but it's going to have at least that many based on our induction hypothesis, right? And so this means that G minus V has at least n1 minus 1 plus n2 minus 1 plus nt minus 1 edges by the strong induction hypothesis. Okay, when we add all these up together, well, the sum of these ni's, n1 plus n2 plus nt, has to add up to all of the other n vertices of the graph except for this vertex v. So the sum of these ni's is going to give you all the total of n. And then we have minus 1 for the first component, minus 1 for the second, all the way to minus 1 for the tth component. So this is going to mean that G minus V has at least n minus t edges. Okay, remember, we're trying to show that G has at least n edges. But we also have to keep in mind that when we deleted this vertex V, we must have deleted at least one edge for each of the components here, right? Because if this were to disconnect the graph, then each of these components would have to be in some way connected back to the vertex V with at least one edge, possibly more, but at least one. And if it didn't disconnect, well, then we only deleted maybe at most or at least one edge, but we couldn't have deleted less than one edge because then the graph wouldn't have been connected in the first place. All right, and so we have that when we add back in the vertex V and its incident edges, we add back in at least one edge for each of these components. So we add back in at least t edges. So the size of the original graph G, where we add V back in, is going to be at least the size of G minus V, which was n minus t, plus t, right? Plus those t new edges that we've included back in, which is n. Well, I ran out of space, but this completes the induction step. And so by the principle of strong induction, we have that the size of every connected graph of order n is at least n minus 1.